Okay, getting back to the question of orientation. Since valence bond theory holds that a bond consists of overlap of orbitals on neighboring atoms, it stands to reason that the extent of overlap would have to do with the strength of the bonds, and that's true. And also that you can get better overlap if the orbitals are pointing right at each other than if they're pointing at an angle towards each other. And that's generally the case. So the orientation for most types of orbitals will affect the amount of overlap you can get. Remember, S-type orbitals are spherical, so orientation doesn't matter with them. But with the the p orbitals, you have px, py, and pz orbitals that are perpendicular to each other. And so in any given situation where two atoms kind of approach each other, you might have one of those p orbitals on each atom that are pointing right towards each other. But then you've got the other p orbitals that are, so you got the two p orbitals that are pointing right at each other, but then the two other p orbitals that will be going straight up and down, perpendicular to those p orbitals that are pointing at each other, like the pencils here. And then you'll have yet another p orbital on each atom that's going horizontally, like this. And so they're not, the other p orbitals are not pointing at each other, and they're not going to have a good time overlapping. And generally, for the best, strongest bond, you want the orbitals pointing right at each other, pointing at it sort of an angle, sort of like that. That doesn't work as well. Okay, so for overlap of the orbitals that are pointed right at each other, you can have an overlap between s orbitals, and that's what you find in hydrogen, sort of like this, what I've drawn here. That area of overlap, that would be considered the bond, and there are two electrons in that area. You can have overlap between an s and a p type orbital, which is what you find in HCl. So that would be like this, a spherical s orbital and the dumbbell shaped p orbital overlapping, and that's where the bond is, right where they overlap. Or you could have a p orbital and a p orbital on two different atoms overlapping end to end, and that would also be a single bond. And that's what you find in chlorine, Cl2, Cl2, or ClCl rather, for Cl2 overall. These bonds that are formed by direct overlap between orbitals that are pointing right at each other are known as sigma bonds. The Greek letter sigma, which looks kind of like an R the way we draw it, but actually it's the Greek equivalent of S, presumably for single, is what we call those bonds that form between either S or S and P or P orbitals when they form by direct overlap of orbitals that are pointed right at each other. Since these orbitals are pointed right at each other, the actual angular orientation of those orbitals doesn't really matter. And so when it comes to single bonds, you actually have free rotation around single bonds. The model kit that I used to build the models of the molecules for the last chapter, I haven't taken them apart yet, so we can use that as an example. The model kits are fairly accurate in this regard. This would be a model of something like CH4 methane with carbon in the center and single bonds to hydrogens all around it, equally spaced in a tetrahedral arrangement. And you can actually take these atoms and twist them relative to each other, and that is a fairly accurate representation of how you can have free rotation around sigma bonds. Okay. On the other hand, we can form what are known as pi bonds. The Greek letter pi, or also the mathematical symbol pi, they're formed by side-to-side overlap of p orbitals, and apparently, that's probably where the why they use the Greek letter pi, because that's the Greek equivalent of p. And figure 8.5 on page 415 or 425 shows you representation of that type of bond a little better than I can draw it. Anyway, well, okay, a lot better than I can draw it. Anyway, it's the, where'd that come from? Anyway, you have the other p orbitals that I was talking about when I was talking about, say, my fingers are p orbitals that are pointing right at each other. They can form a sigma bond with each other, but you also have the other p orbitals, the p orbitals that are both perpendicular to the ones that are pointing right at each other. So the pencils here would be the other p orbitals on the same atoms. And you've actually got a total of 3 p orbitals on each atom. So you can have on each atom, you can actually have the p orbital that's pointed at the other atom. You have a p orbital that's going horizontally 90 degrees to the p orbital that's pointed at the other atom. And you've also got one that's pointed 90 degrees to that, going straight up and down. So you got the one p orbital here, and the second p orbital here, and the third p orbital here. If you get atoms next to each other that have p orbitals that have single electrons in each, you can actually get sort of a side-to-side overlap between those p orbitals. And that would be kind of like having a side-to-side overlap between this p orbital and this p orbital. Okay. And that would be considered a p bond, a pi bond, rather. All right, so the way I usually draw it, they in the book they tend to draw the p orbitals with sort of squat fat lobes, and that really is a more accurate representation, and it's easier to show them overlapping that way. But it's also harder to draw for somebody with zero artistic talent like yours truly. So I tend to draw them with thinner lobes, and I just draw like connections between them like this to represent the pi bond. And since each p orbital has 2 lobes, that would mean that the side-to-side overlap can occur in 2 places. The way I've drawn this p orbital here is I've drawn the p orbital vertical to the bond between the 2 atoms. That is to the sigma bond between the 2 atoms. And so you would have an overlap above the plane of the sigma bond and an overlap below the plane of the sigma bond. And both of those together collectively represent 1 pi bond. So each pi bond has 2 lobes, if you want to call them that. Because this is a side-to-side overlap, you don't have free rotation around pi bonds. So if there's a pi bond present in a molecule, the atoms involved in that bond cannot rotate because you need that side-to-side overlap. If I take these, say the 2 pencils here are the pi bond or the p orbitals that are overlapping side to side to form a pi bond. And if I rotate one of them, they're out of alignment now and they can't overlap anymore. So there's no rotation around a pi bond. The electrons, once the pi bond forms, the electrons will hold the atoms in place and you can't rotate them. Well, you can't rotate them without breaking the bond, and that's not easy. Now, the thing to keep in mind, though, is that pi bonds are only going to form if there's already a sigma bond present. All right? Because the p orbitals have to get close enough together to overlap side to side, and they're not going to be that close together unless there's already a sigma bond holding the atoms together. So a single bond is a sigma bond. An example of that would be Cl2. You know, the chlorine-chlorine bond is formed by the overlap of 2 p orbitals that are pointing right at each other. That's a sigma bond. A double bond would consist of a sigma bond and a pi bond. So what we have here in this molecule here would be a double bond. You got the sigma bond that goes directly between the 2 nuclei, which I've drawn here as just a line, just because the figure would get crowded if I tried to draw in the p orbitals going that way also. But the pi bond is the overlap between the p orbitals that are, you know, side by side with each other. An example of that would be oxygen. Oxygen has a double bond. So it has a sigma bond and a pi bond, and that makes it a double bond. A triple bond would be a sigma bond and 2 pi bonds. Okay, and that's because of the overlap of the p orbitals for the second pi bond is perpendicular to the first. So if you have, there's the fourth one. You've got an atom. Okay. You've got an atom here with a p orbital and another p orbital and a third p orbital. And it's going to form a sigma bond with another p orbital. And you also have perpendicular p orbitals in that other molecule. You've now got yourself a situation where you could have 2 pi bonds. You could have the pi bond between the 2 pencils that are, or p orbitals that are horizontal, and you could have a pi bond between the 2 pencils or p orbitals that are vertical. And that would be a sigma bond, which is this, and 2 pi bonds. And that would be a triple bond. Okay, so the pi bond that makes it a triple bond is perpendicular to the pi bond that makes it a double bond. And so in addition to having a lobe above the the sigma bond between the 2 nuclei and below constituting the first pi bond, the second pi bond would have a lobe that's sort of above the sigma bond between the 2 nuclei and another lobe that's below the sigma bond between the 2 nuclei. So each pi bond has 2 lobes, but it's still only considered 1 bond. And you'd find an example of that in nitrogen. N2 has a triple bond between the nitrogen atoms. The sigma and pi bonds are represented the same in the Lewis structures, because remember we said that as far as the Lewis structure is concerned, you're really only concerned about the amount of space that, well, each of these bonds, a sigma bond and a pi bond, each consists of 2 electrons. And so there's really no way to distinguish them as such in a Lewis structure, except that in a Lewis structure, you know that there must be a pi bond if the 2 atoms are sharing 4 electrons, like in oxygen. Because the oxygen atoms are sharing 4 electrons, you know that means a double bond. And so now we know that one of those bonds is a sigma and the other one is a pi bond. Or if you draw Lewis structures like this with lines representing the bonds, again, a double bond consists of 2 lines, but there's no way to tell which of those lines is the sigma bond and which is the pi bond. And in fact, as far as the Lewis structure goes, it doesn't matter. Okay, it's just what matters is that there's a double bond. And the double bond is 1 sigma and 1 pi. So in terms of strength, a triple bond is stronger than a double bond, and a double bond is stronger than a single bond, but length goes the other way around. So the strongest bond is also the shortest, and the weakest bond is also the longest. Interesting, though, to separate sigma and pi bonds, because the reason that a double bond is stronger than a single bond is that a double bond consists of a sigma bond and a pi bond. So of course, a sigma and a pi bond will be stronger than just a sigma bond. Makes sense. But it's not twice as strong. So individually, if you were able to take a pi bond on its own without a sigma bond, which doesn't actually exist, but if you could, the pi bond would actually be weaker than a sigma bond. So it increases, adding a pi bond to a sigma bond increases the strength of the bond, but it doesn't double. Adding 2 pi bonds to form a triple bond, again, increases the strength of the bond, but it doesn't triple it. So pi is weaker than sigma, but triple is stronger than double, which is stronger than single, because a triple is a combination of sigma and 2 pi bonds, and a double is a combination of a sigma and a pi. All right, now, the question of why certain shapes of molecules form when those shapes are different from the shapes of the atomic orbitals where the electrons that form the bonds are located is addressed by what's known as hybridization of atomic orbitals. So if the orbitals were used, if the orbitals used to form the bonds in a molecule were just S, P, D, and F, those shapes that we saw in the last, chapter 6, rather, then only certain shapes of molecules would be possible, and the bond angles would be almost all 90 degrees or 180 degrees, one or the other. Well, we've got all kinds of different bond angles, as we saw. We've got 120 degrees, and we've got 109.5 degrees, and a bunch of other and a bunch of other angles too. And the question is, why would that be? According, looking at the Lewis structure and the VSEPR structure too, for that matter, you would expect that water should have a bond angle from hydrogen through oxygen back to the other hydrogen of 90 degrees, because it's the p orbital on the oxygen that's bonding to the s orbital in the hydrogen, and the lobes of the p orbitals are 90 degrees to each other. So if you've got hydrogen attaching to the lobe of one of the p orbitals and another hydrogen attaching to the lobe of another p orbital, that angle should be 90 degrees. But the actual bond angle is 104.5 degrees, which is quite a distance away from 90. And so the question is, again, why? Why do we get a molecule in a shape that really shouldn't exist? And the conclusion was, well, the orbitals that form the bonds in the molecule must be different somehow from the orbitals that are found on free atoms that are not involved in bonds, the s, p, d, and f orbitals. And the conclusion was that what happens is that the atomic orbitals hybridize when forming molecules, and hybridization is just sort of a combination of atomic orbitals of different types and shapes into hybrid orbitals with shapes that are sort of a combination of the shapes of the orbitals that went into the hybrid. And they're named, the hybridized orbitals are named for the atomic orbitals that are involved in the hybridization. So a good example is, again, H2O. We already saw that it has a bond angle that's way off from what it should be, according to what we've seen so far. The valence orbitals in oxygen are a 2s, and the 3 p-type orbitals of the second shell, 2px, 2py, and 2pz. So you've got a total of 4 orbitals, 2 types of orbitals, but 4 individual orbitals in the valence shell of oxygen. When forming molecules, they hybridize and form what's known as an sp3 hybrid orbital. And it's called sp3 because it's a combination of an s orbital and 3 p orbitals. So spp or sp3. Okay. The shape is tetrahedral. That's the shape of this hybridized sp3 orbital. And the bond angles ideally are 109.5 degrees, which you'll notice is a lot closer to 104.5 than 90 is. So we're getting somewhere now. And the difference between the 104.5 and the 109.5 is just because of the extra repulsion of the lone pairs on the oxygen. That right there is enough to explain the difference between 109.5 and 104.5. It is not enough to explain the difference between 90 and 104.5. Okay, so the VSEPR electron geometry for H2O, that is tetrahedral. And that happens to be the geometry of an sp3 hybridized set of orbitals. And that's because oxygen actually has an sp3 type hybridized set of orbitals in H2O. Okay, and of course, as we all already established, the molecular geometry for H2O is bent, because when we're naming the molecular geometry, we don't count the lone pairs. So you have your oxygen, and you have your badly drawn tetrahedral lobes of the sp3 orbitals, and a hydrogen will, with its s orbitals, will attach to one of those lobes, and another hydrogen with its s orbital will attach to another one of those lobes, and the other two lobes will be lone pairs. Or you could draw it with a sort of just showing the shape. You can draw it sort of like this. And you notice the hydrogens are bent relative to the oxygen, and the lone pairs occupy positions that fill out the tetrahedron. But of course, when we come to name the molecular shape, we don't count the lone pairs, and so we end up with something like this, bent, in other words. Okay, so this is the kind of thing that happens a lot when forming molecules. And there is a wide variety of different types of hybrid orbitals that can form. And each type of hybrid orbital gives you a different shape for the arrangement of electrons around the central atom. And of course, that is ultimately what decides the shape of the molecule. So the type of hybrid orbital is intimately related to the electron geometry of the molecule. And that, of course, is intimately related to the molecular geometry of the molecule. Hybrid orbitals, a couple things about them. First of all, remember, they don't exist in free atoms. They only exist in bonded atoms. So hybridization doesn't occur until you're about to form a bond and form a molecule. The shapes are different from atomic orbitals involved, but they're named for the atomic orbitals that go into making them. The number of hybrid orbitals is equal to the number of atomic orbitals that are hybridized in order to create them. And you can also get the number of individual atomic orbitals that are involved by looking at the name of the hybrid. Like in the sp3 hybrid, sp3, like 1s and 3p's, means that there are a total of 4 orbitals involved in that type of hybridization. And 4 orbitals means 4 pairs of electrons, or 4 regions of electrons anyway, around the central atom. And sure enough, sp3 has 4 orbitals involved in its name, and there are 4 regions of electrons around the central atom. And that gives you a tetrahedral electron pair arrangement. And it works the same way with all of the other types of hybridization that we'll see in the near future. Let's see, all of the individual orbitals in a set of hybrid orbitals are equal in size and shape and energy. I didn't draw this very well here, but all of the lobes in this sp3 hybrid set of orbitals should be the same size and the same shape, and they all have the same energy. Okay. The types of the hybrid orbitals in a molecule correspond to its electron geometry and vice versa. So if you know what type of hybridization is involved in the central atom of a molecule, you know what its electron geometry is, and vice versa. If you know what its electron geometry is, you know what type of hybridization is involved. So if the central atom is sp3 hybridized, that means it has a tetrahedral electron geometry around the central atom. And if it has a tetrahedral electron geometry around the central atom, it must be sp3 hybridized. Goes both ways. Hybrid orbitals are used in forming sigma bonds only. Pi bonds are formed by unhybridized p orbitals. So that's something to keep in mind. If you're talking hybrid orbitals, you're talking sigma bonds. Pi bonds, which can exist in the same molecule or even between the same 2 atoms as hybridized orbitals forming sigma bonds, but the pi bonds will involve only unhybridized p orbitals. Okay, so that's kind of a different thing. Looking briefly at the types of hybridization, we'll start at the bottom with the simplest one, and that would be sp hybridization. Sp hybridization is a hybridization that involves an s orbital and a p orbital in the valence shell of the central atom. And remember that the number of orbitals involved in the hybrid is the same as the number of electron regions on the central atom. And that means if you've got two orbitals involved in the hybridization, then you have two regions of electrons on the central atom in this type of hybridization. Okay. And that means that your electron geometry must be linear. Because if you've got a central point and you've got something on one side and something on the other side, the way that you can get those two things on either side as far apart from each other as possible is if they're 180 degrees apart, directly opposite each other. And that would be a linear electron geometry. An example of that would be beryllium chloride, or BeCl2. The beryllium has one single bond to each chlorine. And what I've drawn here is getting it closer actually makes it more blurry, unfortunately. But this is shown in the textbook also, so you can look at the what they've shown there. You've got a p orbital on the beryllium, or sorry, and an s orbital on the beryllium, and the p and the s orbital hybridize to form these two lobes of a hybrid orbital. And when you combine them together, you get the beryllium at the center, and you have these two lobes of the hybridized sp orbital that are pointing outward exactly opposite each other, and they can engage in sigma bonding with the p orbitals from the chlorine. Some other examples of sp hybridization would be any triple bonded carbon, like in acetylene. So you got a triple bonded carbon and a hydrogen that sticks out one end and a hydrogen that sticks directly out the other end. That is a linear arrangement. Each carbon in this molecule would be an sp hybrid. This is an example of a molecule that doesn't really have one central atom. So you can kind of look at the carbons individually as central atoms. So if you look at the carbon on the left as a central atom, then the hydrogen would be an outer atom, and the CH would be like an outer atom. And the arrangement around the carbon on the left is linear. And it's the same thing in reverse for the carbon on the right, linear. Carbon with two double bonds would also be an sp hybrid, like in carbon dioxide. We end up with one region of electrons, two regions of electrons, no other regions of electrons on the carbon. And so the two regions of electrons will get 180 degrees apart from each other, and the molecule will be linear. So that's an sp hybrid on the carbon. Looking at the orbital energy diagrams, what happens here in terms of energy is that the valence shell of the beryllium has two electrons in the 2s orbital and no electrons in the 2p orbitals. And the hybridization involves the 2s orbital and one of the 2p orbitals, and you get two sp hybrid orbitals of equal energy to each other. The energy is higher than the energy of the 2s orbital, but lower than the energy of the 2p orbitals. So the energy is kind of between the two orbitals that were hybridized. And each of those will have one electron in them. That allows these electrons to sort of spread out so that there's one electron per orbital. And that is how beryllium ends up forming two bonds. One electron from a chlorine, in this case, would pair up with this electron, and an electron from the other chlorine would pair up with this electron. Okay, and you still have left over the two 2p orbitals that have not hybridized. So they're still there. They're empty, but they're there. And if this didn't happen, there'd be really no reason why beryllium would want to form any bonds, because it has two electrons in the s orbital of the second shell. That s orbital is filled, and it should be fairly content that way. It's got two valence electrons like helium does. And it's the fact that it can form these hybrids and split those electrons up into lone electrons in two different orbitals. That's why it can form bonds. The next type of hybrid we will get to in the next part of the video, because I see we're over time now. So we'll come back and start with sp2 hybrids, getting a little more ambitious now.